Hello everybody, welcome to my next session in my Data Science with Mathematica track. Today I will be giving an introduction to reinforcement learning. This is one of the three main areas of machine learning and is probably the most flexible way to model things and also extremely applicable because basically it is the science of learning and it is the science of decision making. So I will start out by introducing the basic ideas and principles that we have in reinforcement learning, and then I will make a distinction between tabular and approximative methods. It's very important to make that distinction because there are many things. Most real-life applications are too big in order to store them in memory. And there's also problems of infinite size. So there is no way to tabulate everything that we have to deal with. I will then use the simple game of Tic-Tac-Toe in order to illustrate some of these ideas and to fully compute through several solutions with that as a tabular method and as an approximative method. Okay, so before we begin, and I have to ask you to bear with me for a while, I need to set some basic definitions and introduction before we can get to the actual simple example. Bear with me, I think it's important to make this introduction rather thoroughly, even though it will probably take a bit of time. So with reinforcement learning, where are we in the overall machine learning landscape? And I think the best way to show this map is from a talk given by Andy Jassy. He is the CEO of AWS. He showed this map on a keynote on reInvent 2018 in Las Vegas. Reinforcement learning generally means a high degree of sophistication and a low amount of training data needed, unlike supervised learning, neural networks, for example, or deep learning with deep neural networks. So we have two dimensions here, the amount of training data required and the sophistication of models. And with reinforcement learning, we generally find that the amount of training data required is very low and the sophistication of models is rather high, unlike supervised learning or unsupervised learning, which perform different functions but are also very important in machine learning. So more specifically, what we have with machine learning is that in supervised learning we have labeled data, we use labeled data, we are getting direct feedback from our models and we can predict an outcome, for example, something in the future or current observations. The other pillar is unsupervised learning. That's where we don't have any labels for our data. There's no feedback, but it is still very applicable and important because it allows us to find hidden structure in the data. What are you going to do with all your data? Data itself is not valuable. Nobody just wants just data. It's a drag, it's a cost. But in order to be able to make actionable decisions and to get actionable insight, you need to find the hidden structures in your data, and unsupervised learning fits the category for this, right? You need to follow the path that you start with data. From data, you need to extract the information. From information, you can now get insight or comprehension, and that allows you to make management decisions. You can now perform certain actions. But on this path, you need to grow from data to information, to insight, to comprehension. And this is where unsupervised learning helps you a lot to find the information and insight in your data. And then finally, reinforcement learning. This is the science of decision making. You're interested in a decision process, and we will soon learn that this is the agent. The agent is one part of reinforcement learning that will be doing the decision making for us. It requires a reward system. You need to receive certain rewards for the actions that you are performing. and then you can learn a series of actions. This is why it is called reinforcement learning, because you're getting a sequence of signals, you're getting certain rewards, and over time you're trying to maximize a certain value function that is based on the accumulation of the rewards. Okay, and I do point out that very often supervised learning can perform a lot of subtasks in reinforcement learning. These three are not totally separate. Very often neural networks perform great subfunctions for reinforcement learning. For example, we've seen that very successfully with AlphaZero and AlphaGo by the British DeepMind company when they developed the best Go and chess programs that are around. They use reinforcement learning, but they have two neural networks for subtasks. Okay, so the basics of reinforcement learning, we need to understand reinforcement learning is essentially the science of decision making. This is what we want. This is why we are so interested in this. We want to do our decision making a bit more automated and a bit more scientific. And reinforcement learning relies on a basic hypothesis, and that's called the reward hypothesis. And that is that all goals can be described by the maximization of a certain expected cumulative reward. This is a basic working hypothesis. And it is, of course, debatable whether or not this is always realistic or ethical. Can we always describe everything we want to do or automate by cumulative rewards? Is this always possible? Is this always feasible? Is this maybe too simplistic? And is the mechanics for this maybe not doable? Do we have certain problems where we need to do more? Maybe this simple hypothesis just doesn't apply properly for the mechanisms that we need to use in order to solve our problems. So this is a basic reward hypothesis, and it is debatable whether or not it always applies, and you have to check back with it. Is this applicable for your particular problem? Do you need more? But it is a basic working hypothesis that is needed for all the mechanisms that we're going to be developing with reinforcement learning. So the basic idea is that we interact with the environment and we receive certain signals, and then we try to understand these signals and manage these signals and perform certain actions to achieve goals, right? This is going to be the agent. So the learning from interaction is a general foundational idea underlying nearly all theories of learning and intelligence. This is how it works. You interact with something. It can be a computer program, it can be your teacher, your instructor, can be your TA in college. It can be a mouse that needs to open certain doors in order to get a piece of cheese, and when it opens the right doors it gets the cheese. When it opens the wrong door it doesn't get any cheese, right? It's a basic system of interaction, and you're getting rewards based on the basic reward hypothesis. And I had already mentioned, oftentimes it uses supervised learning, neural networks or deep neural networks for subtasks. This is very important, and oftentimes the only way in order to let our agent work. Okay, and more specifically, in a numeric sense, reinforcement learning is learning what to do. What actions do we want to do? What actions do we not want to do? We're doing this by relating certain situations and states to actions so as to maximize a certain numeric reward signal. So the learner is not told what actions to take, but instead must discover which actions yield the greatest reward by trying them. We have to explore our entire exploration space. We have to try out several things and then look at these signals that we're going to get from the environment. So we need a goal-seeking agent, and the agents in reinforcement learning have goals. They can sense aspects of the environment and choose actions to influence the environment. And here in a chart we have basically this process diagram. The agent performs certain actions and they influence the environment. And the environment will give us reward signals, and it will also give us a certain state, and that is perceived by the agent. And we keep going in this cycle until we have a policy that is appropriate and hopefully optimal. So I will want to make a distinction here between state and environment. The environment is the overall environment, right? It can be a computer code base, it can be the outside environment, it can be a factory. So the environment is something within which the agent operates, but specifically state is used in reinforcement learning to indicate those parts of the environment that can be perceived by the agent, right? Not everything of the environment can be perceived by the agent, and also not everything of the environment is important for the agent. But a certain machine in an assembly belt, we can perhaps measure a temperature, right? So that would be a state signal. The entire environment is too much. We cannot measure everything, we cannot know everything, and we also don't want everything. But state, think of state as that part of the environment that can be perceived by the agent, and that is important for the decision making of the agent. All right, and the examples of reinforcement learning are so varied, we find them pretty much in every aspect of human life. I've just written down several examples. I could go on for this. I could fill pages and pages and pages of this, right? Robotics, of course, needs to use reinforcement learning. Otherwise, the robots don't know what to do and do something totally crazy. A lot of game playing is based on reinforcement learning. We need the agent to learn what actions to take in order to get a reward signal, probably points, right? You're probably collecting points for shooting down aliens or for making good moves in chess or whatever the game is. Babies and animals, when they were just born, start interacting with the environment, they receive certain signals, and after a while can perform certain things on their own, sometimes very, very quick. When a foal is born, then after half an hour, the foal is ready to stand on its 4 legs and start running. So monkeys seeking cheese, I've mentioned that. Flying maneuvers in a helio drone. Control systems, we humans as well do that, right? For example, a cooking recipe is something for reinforcement learning. We find out that certain things work, certain things don't, and then you change your policy so that next time your soup is not burned or it's not too salty or whatever need to do. Multiple choice quizzes can be that, right? There are certain multiple choice quizzes where you just try a different answer, and you try it again and again and again until you figure out the right answer. Whether or not you actually learn something during those multiple choice tests is a different question, but you can, when there is a redo possible, you can do it as much as you want and always score 100%. Many logistic questions in portfolio management and financial trading systems. It's pretty easy, and here also the reward function is very easy. It's probably some type of currency, US dollar or the euro or the Swedish krona, some type of reward that is be given in financial terms in a currency. But also in medicine and, for example, in genetic research, protein folding. So many examples that we have here. I think reinforcement learning is pretty much everywhere in our human life. So I mentioned specifically that reinforcement learning always we need a policy, we need a decision-making policy, we need a reward signal, we need a value function. And optionally, we need a model of the environment. Some models in reinforcement learning have an environment model, and some methods in reinforcement learning do not have an environmental model. It is therefore only an optional task. Very often we of course do it. How are we gonna play games when we don't know the rules of the game, or when we don't have any idea how to mimic the behavior of the opponent? But environment is not always available. And reinforcement learning heavily relies on the concept of state. It's an input to policy and value function, and as both input to and output from the model, right? The environment goes into the model, and by changing the environment, it also becomes an output, because with our interactions, we hopefully change the environment, we hopefully influence it. Informally, state describes the environment as it can be perceived by our agent. So next, I want to point out that the methods in reinforcement learning are really the intersection of many areas of science that we are already familiar with. Many things in this chart we have learned already in our undergraduate classes, right? It goes into computer sciences, it needs parts of engineering, it needs obviously mathematics, we need parts of economics, we need optimal control, machine learning, and we can also understand it much better if we have a mindset that uses thoughts and principles from neuroscience and psychology. And the intersection of these several areas of human science then give us reinforcement learning. So this means reinforcement learning is really like trial and error learning. You try something, you see if it worked or not. So the agent should discover a good policy, right? It needs to find it, and we need to use trial and error for that. We need to explore our environment. It uses experiences from the environment. That is really learning, right? When we see what works and what doesn't work, that is a learning. And it hopefully can be done without losing too much reward along the way. Sometimes experiments will cost us money, so we're decreasing the reward. So we need a certain balance of exploration and exploitation. We want to exploit what's good for us, but we also need to explore the entire environment. We need to explore the entire space of choices that we have, because with different choices, we may get more reward. And when we get small rewards, then there are others that may give us more, and also sometimes we can minimize our losses, because, as I said earlier, a reward can also be negative. So we select actions to maximize the total future reward, and these actions may have long-term consequences. It's not just the immediate reward. We really have to create cumulatively discounted sum of these rewards, and that becomes the value function then. Value is the cumulation of rewards. The rewards may be delayed. We may not be able to get something out of it immediately. And rewards can be negative. And this is particularly useful for us when we want to model something that is I call them in minimum time problem. For example, in the Deep Racer League by AWS, that robot car race, you are losing points for taking too long, because the winner is the one who does it in minimum time. So you could lose, for example, something like 2 points or 5 points or 10 points for every second that you are in the race. So now when you're doing your reward maximization, you're seeking a solution that tries to minimize the time delay, right? So whenever something has the character of a race, then time steps could be receiving negative rewards. All right. So, and very often it may be better to sacrifice an immediate reward to gain more long-term reward. We have that, for example, in financial investments, right? You're putting down $10,000 right now in order to get $15,000 in, 5 years or 10 years, whatever the interest rate is. It can also be applicable when it's important to interrupt a mission very early to prevent a disaster. For example, you may have to make an intermediate landing of a drone or of a plane when you are about to run out of fuel, right? You may have to abort the mission, because if your plane crashes because it's running out of fuel, it's a pretty negative reward. So you may get better reward situation when you interrupt the mission early. And there are many ways to model this and to have it. In chess, for example, a reward can be received for blocking an opponent move. One of the many chess strategies is to really lock in your opponent, make it impossible for your opponent to move. You really want to totally build a wall around them so that they have no more moves available, right? Blocking opponent moves, that can give you a reward. It can also be sacrifices in chess or shogi or in other games. And one of the stunning discoveries that we had with AlphaZero was that many very early sacrifices and sometimes really valuable pieces have provided a future positional advantage that secured a win. That was one of the big surprises that we saw in the book Game Changer that I highly recommend, that the AlphaZero was making several early positional sacrifices. And no human could immediately understand it until the game was played fully out. And then it's possible to understand, well, sacrificing these pawns and even sacrificing this bishop was a smart move. So all this can be modeled with intelligent reward and value functions. Keep in mind there can be negative sacrifices, can be a smart way to do that, and also lose points for taking longer to finish something. So I had already mentioned reinforcement learning uses many fields that we are already familiar with from undergrad. For example, one of the main pillars is Markov decision processes that we have. And planning is oftentimes done with dynamic programming. Now that can be expensive. Dynamic programming can be very computationally expensive, but it also, when it is doable, is a very smart strategy. It is based on the Bellman equations, and sometimes that's called the principle of optimality. And when you use Bellman and the principle of optimality, you can be assured that your sub-problems, your sub-tasks are already optimal. That's what dynamic programming is based upon. And one of the other words used for dynamic programming is actually recursive optimization, and that is what it is. And you can only do recursive optimization if you can create optimal sub-stages for every stage that you have in the overall dynamic programming objective. We use Monte Carlo methods, and that's for prediction, for estimation and control. We will be looking today at temporal difference learning. That means that you try something and a time step later you know a little bit more. You may have better rewards, have a better value function. You've learned something by going from time step t to time step t+1. Bootstrapping, combinatorial optimization, model 3 prediction, model 3 control. We use function approximation, gradient methods, learning and planning, and as I already have mentioned, exploration versus exploitation. So we use many different fields. There's really nothing in reinforcement learning that is now totally separate and new, right? We are bringing several areas of science together and use an agent to explore what the optimal policy is going to be. So at this point, I want to split this into two types of methods. We have the tabular methods, and those are applicable and actually the most efficient way to do all of this when we have action and state spaces that are small enough for the value functions to be represented as arrays or table. So they fit in memory. And sometimes that can also be disk space. But we can use table structures or arrays in order to fit everything in some type of memory. And then these methods can sometimes find exact or optimal solutions and yield us an optimal policy. That's what we want. That's what we are ultimately after. We want to have an optimal policy for our decision making. But we have to use approximative method when the action or state space is too large to be represented as arrays or table. We have no choice. There are so many things that have a combinatorial explosion, again like chess or shogi or go or many other things. So we have no choice but to use approximative methods for very large problems, and it's also the only way to handle infinite problems. There can be state spaces that are infinite. So with the next, I want to look closer at the tabular solution methods and look at tic-tac-toe in particular as our problem. Before I begin, I want to make a distinction on terminology. I call certain things bottom-up and certain things top-down. So bottom-up is when you start with everything and you work your way upwards towards an optimal solution. And top-down is when you start with the optimal solution and you work your way backwards in order to find paths that bring you to that optimal solution. You can imagine this like a tree or a pyramid, and top-down means you start at the apex of the pyramid and work your way downward, and bottom-up is you start at the bottom and work yourself upwards. And we will see that very often top-down is much more efficient. You have less data to deal with and you can prune the tree and make things much more efficient because certain things just don't contribute towards an optimal solution. And bottom up, you will have even those useless states and paths that you need to deal with in your computation and in the exploration of your space. So bottom up is generally computational more demanding, and it also requires more state and more computation time and more memory. Okay, top down means you start with the end solutions with the wins and you work yourself backwards. So this has several advantages. It reduces the number of candidates that intermediate nodes have to be computed, and many states have no chance to contribute towards a sensible solution. There can be entire branches and paths that are cut off when you look at the non-winning end positions. So they should be included from the get-go, right? Why handle stuff that never helps you, that just doesn't bring you to a winning solution? Don't handle things you don't need to handle. And this may not always be a lot, it depends on the problem. So today in our tic-tac-toe example, we're gonna see it's really not a lot, but most problems are not gonna be as simple as tic-tac-toe. So this way we avoid paths that lead to a draw. We prefer wins over draws, right? We want to win. So in some sense we can say a draw is just as bad as a lose. And if you have this mindset, then top-down is the way for you to go if it does fit in memory. So to check and to test whether or not an intermediate node is optimal, it may also take time, and it needs to be done much more if you go bottom up, right? So you again save a lot of computation time, data and memory consumption if you go top down. So let's start with simple tic-tac-toe example. I picked tic-tac-toe because it's so simple that everybody knows it, but we still have something like 282,000 paths that are possible, that are feasible. So that's why I think tic-tac-toe is a certain sweet spot for simplicity, but at the same time also having certain computational demand. And I think everybody knows it. It's simple enough to be understood by everyone. So let's create, for example, all the positions that we have. We have a couple of sample positions here that indicate a win for cross. So we move first and we are the X, we are the cross. And our opponent is the O and they move after us. This is a general working assumption. It is like chess. White always begins and then black makes the second move. So just like in chess, we are white and make the first move. We are here X and make the first move. And I narrow it down to this by saying that the count of the X's minus the count of the O's has to be 1, right? So there is always 1 X more than there is O's. So we have these patterns here, and these are the winning positions that we have. When A is an X, that's us making the first move. The first move here is in count X minus count O is 1. And here we have the patterns. So for example, the first row or the center row, the last row, the diagonal from northwest to southeast, the center column, the right column, here we have a diagonal again from northwest to, no, from northeast to southwest, right? These are the winning positions, and that is all of them. It's a long list. Just want to show you what I mean with the winning positions. So here I put them into opt. We are looking at length of opt, and we see there are almost 700 winning positions for X. So we also want to compute a loose, and I also want to have a certain grid formatting function a little bit later. Okay, so when you can play a game to the end and you can catalog all winning solutions, then such a game is called solved. Obviously, tic-tac-toe is solved, but chess is not solved. Go is not solved. Shogi is not solved. So with tic-tac-toe, we can certainly do that. We were able to pre-compute everything and store it in opt in pretty much no time. I mean, we have already computed all of them. So in those cases, to get all the game paths to a winning position, it is most efficient to start with the end position and work backwards ahead. I already mentioned that. That way, we don't even have to handle any intermediate positions and paths that do not lead to a winning solution. And for our purpose now, that's a lose or a draw. And you may know from other sessions, one of my general principles is don't handle what you already know you'll never need. Right? If you know it doesn't help, it doesn't contribute, then don't even handle it. It saves computation time and memory. Try to use parsimonious on your resources. And this will be different later on when we cannot pre-compute everything, but we have to explore much more. But when it's possible, by all means, do it. So oftentimes, however, this is not the only way to do it. You can't always pre-compute all winning solutions. Again, I frequently mention chess because I've looked at Game Changer a little bit closer. And even if you can, then you can't backtrack all the way to the beginning. So the number of paths would increase with an explosion of combinatorial possibilities, so you can't do that. So here I start with the winning positions of the game. You see that I start with opt. That was all the winning positions. I do that, and then for each item we compute the immediate predecessors. So I'm setting up an association that I call predecessors. So when we compute this, then we have as keys the nodes, and as values we have all the predecessors that are available for all these node states. That is a number, make a note of it, it's 5,718. You see that here in this data set. So you see here, these are the keys, and on the right we have the predecessors that we have with this. So given that it's predecessors, we have a lot of predecessors for a board that's rather filled, as you find at the end of this association, of this data set, and we have short ones when we start with short keys. For example, if we have one X and one O, then there is only one predecessor, and that was the X, because we go first and the opponent goes second, right? And when we have a rather long, here for example we have all 9 fields filled, so we have rather long predecessors here in our predecessor list. Okay, make a note of it, it's 5,700. But next we need the opposite. We want an association of all successors, not predecessors. And we start with the end and we exclude anything that doesn't lead to a winning position. Again, I call that top-down, and here I'm also using TD for top-down as the name of our association variable. So TD is now the exact opposite. We have as keys the positions, and as values we have all the successors. So for example, when we start with X, then we have all these cases with an O as the second move, right? So you see all the other possibilities here that are available. The X is us, we make the first move, the opponent is O, so you see as values all these possibilities where the opponent has made a move. So we have only 2 fields filled. And again, at the end, these are shorter, because when you have a position that is rather filled as a key, then you only have 1 or 2 successors as a possibility with that. Okay, but later today we'll also need the paths that are computed starting out at the bottom and grow upwards. This is bottom up. And we also need a bottom up association, and I call it BU. And please note that here we already have much more in this bottom up association. We have over 6,000 elements in this association. Right, so it's about 300 more than we had in top down. Again, 300 doesn't sound much, but not everything you'll be doing in reinforcement learning is gonna be tic-tac-toe. So 300 now is, well, definitely enough to explain the point that we want to prefer top-down if this is possible. Okay, but now that we have this, let's compute all the paths from the starting positions to the winning positions, and I do it both ways. I do it with TD and I do it with BU. And also note the time, it's about a second faster. So we start with all the initial positions that we have, and we use TD top down. And after 5.58 seconds, we have computed all the paths. Again, I start with all the positions that have 1x, our first move, and I will store them in paths. All of them together will be, I think, 282,000 or something like that. So here I'm creating these paths and I keep appending to them, and my data input is TD, top down. And when we have computed this, I need to explain these paths. So path 5 means that we have a winning position where we have 5 fields marked on the board. And given that we go first, this can only be 3 X's and 2 O's, right? Because we go first and we are X. So 3X and 2 O's. Path 6 now means that it has to be 3X and 3O, because after we make our move, the opponent has a move and the opponent is O. So path 6 will be those paths where we want to filter out those positions that we lose. So we have used 3x and we didn't win, but the opponent has successfully put 3 X's in a row, column, or diagonal, right? Path 7 again is an odd number, so we have made the next move. We're interested in our wins, so we are looking up in the optimal solution and keep those paths, and 8 and 9 and so forth, all right? And then I always subtract them from paths. You always see that paths is the complement of paths and what we have just created as an optimal solution, so win or lose. And that gives us now the following distribution. So with 5 fields marked, we have over 34,000 winning solutions. The opponent wins with 3 O's and 23,000 solution. We win with 4 fields in almost 96,000 and so on. And also note that this way we don't have any draws, because paths, after we keep subtracting here from paths, leaves nothing left. That means we have only winning solutions, losing solutions, no draws. All right, so let's look at some random examples by length. So with paths of 5, we have here all the solutions where we have exactly 3x and 2o, and all of them we have 1. With path 6, we now have losing positions, because we have 3x that didn't give us a win, but the opponent has successfully brought in 3 O's in a column, in a row, or on a diagonal. Right? These are random positions that we have taken here. With path 7, again, we are winning 4x 3o. Path 8, we have again lost because we didn't win with 4x. The opponent has won with 4o. And the same with 9. Here we needed the entire field in order to win. Right? Here you see we have 5x, the opponent has 4o, and we have 1 in rows, columns, or diagonals. All right, so let's look at some statistics. And when we look at these statistics, we can see that we have more choices for a winning position if we are computing according to the scheme that I've described, if we start in the middle, because now we have over 5,700 paths in order to get to this position. And we see that the first four, the lowest ones, are when we start in the north, west, east, or west positions. Then we only have 2880. We have a few more choices if we take the corners: northwest, northeast, southwest, southeast, and greatest path, greatest flexibility we have if we start in the middle. Now, regarding the losing games, if we start anywhere on the board, then that gives the same number of paths to a losing position. Here it doesn't matter, it's always the same number, almost 2600. Now, if we want to win with 7 pieces, with 7 markings on the field, that means 4 X's and 3 O's, then we have a similar story. We have the greatest degree of flexibility if we start in the middle, and we have the smallest, the lowest number of paths if we start in the northeast, southwest position, and somewhat in the middle if we start in the corners. So then again, if we want to lose with 8 pieces, that's 4 plus 4, again, it doesn't matter, it's always the same number. And if we want to win with 9 markings, that's 5 plus 4, we have the interesting observation that when we start in the north, east, southwest corners, then we actually have these 4 possibilities with the highest number of wins. And the corners then follow second place with 8,784, and in the middle actually gives us the lowest, right? But usually we probably want to win quickly. That's why paths 5 would be of greatest interest. But I think you may find it unintuitive that if you want to win with 9, it's exactly the opposite situation. We should start in north, east, southwest positions, and we get the lowest number of possibilities if we start in the middle. So I've summarized these observations here. Paths 5, we want to win quickly. That means with only 3x and 2o. And I think we kind of knew that intuitively, that starting in the middle would be best. That is in this case here. It's the largest number that we have here. It gives us the greatest flexibility for all the subsequent moves. We'll have 7 choices after that opponent move is made. And that is because we start with 1, the opponent places another 1. Now 2 fields are gone, that leaves us 7 choices. So if we start in the middle, we can potentially win 1 row, column, and 2 diagonals with that. If we start in the corners, we have fewer possibilities. We can potentially win 1 row, 1 column, 1 diagonal with that. If we start in the north, south, east, west positions, we can only win 1 row and 1 column. So we have fewer choices. If you want to lose with 3x and 3o, it doesn't matter where we start. All the 9 elements are equal. That's this row. If you want to win the 7 markings, then it's the same story as in the first row. If you want to lose with 4 and 4, it's the same as with 3 and 3. And the interesting part, if we want to win with all 9 markings filled, that's 5 plus 4. It's actually harder for us if we start in the middle, but not by much. These numbers here don't differ all that much. They are much more varied here in the first row. Here the numbers are much closer, but it's still the case that the center position gives us the lowest number of possibilities. So, all right, next I would like to do the very same thing with bottom up. Note that the time takes a little bit longer. And if we now look at the paths, we now have over 46,000 draws, right? So here again, we look at paths in this list, and we see paths now includes over 46,000 draws. Again, that's because bottom up it starts at the bottom and includes so many useless possibilities and so many paths and positions that don't help us towards a win. That's why bottom-up is so inefficient. We have so many cases here that we don't really want. We want to win. We don't even want a draw. But if we do bottom-up, we have to consider it, because we cannot force a win when we have to start from the bottom. So as we look at this, we now have over 46,000 positions here in the last variable paths here. Okay, so let's look at some random examples again. We are looking at them by the path length. Again, the first one is 5, so it's 3x and 2o. This is where we win with 5. The next row is where we lose with 6. That means we had a 3x and couldn't bring it to a win, but the opponent was winning to bring us to a lose, right? And that can be a row, that can be a column, it can be a diagonal. So interesting here is, I think, particularly the last row, where we see all of these are draws, right? Neither side could win. We couldn't win, the opponent couldn't win. All of these are 46,000 paths towards a draw. Okay, and some statistics when we're using bottom-up, and it is somewhat similar to what we had when we did top-down. The numbers for lose are no longer the same. Okay, you see that here we have lose and they are not the same. And all the numbers with BU are never less than the TD numbers. This is also important to note, because we have to handle so much data. They're the same or higher. So when you compare this row with the TD row, the numbers are the same or higher. And this row, it's the same or higher. So for all of them, it's the same or higher. They're never less than the TD numbers. And we have draws as a possibility, right? So these numbers are a little bit different. So this brings me to the big conclusion. With bottom-up, we have more stuff to deal with and manage. Computations take longer. We need more in data memory, and we have to handle more non-winning positions. That's losses and draws. So again, let's look at this a little bit closer. Let's do a comparison on the sizes of these associations or data sets. I'll call those ones useless when we have them in the values of bottom-up, but they're not in the values of top-down, and we restrict it to our move, one move ahead of the opponent, right? So it's 1x more than we have O's. And I subtract them with complement, that is really the set minus function in Mathematica, and we get 118 that are completely useless. Again, 118 is not a lot, but most problems are not tic-tac-toe. But none of these 118 positions was ever used towards a win. None of them. Never occurred on a path. It was never a state that contributed towards a win. It was there and we dealt with it in BU, but we didn't deal with it in TD. It was basically wasted effort. Okay, and I want to point out something about the sizes here. It's also clear that this is always 7 or 9, because if we have less than 7, then there is no winning position yet, and it obviously can't be more than 9, because the entire game has only 9 fields. So we have this situation here that we have 90 cases where we have 7 on the field, and we have 28 positions where we have 9 on the field. This is exactly these 118 here that we're looking at. Okay, and it's also very clear why we have that. That's because we always need to have at least 5, because with 1x more than 1o and 3 required to win, we need to have at least 5. Right? Anything less than 5 is impossible. We never have a win if we don't have at least 5 markings on the board. So when we join everything from TD, we get over 5,700, and everything from BU is over 6,000. And when we look at the actual length of the keys and the values, we see the same story. We have much more values in BU than we have values in TD. What is this? Something like maybe 1200, maybe 1200 is a difference between those here. All right, so now let's go towards the strategies that do not use pre-computation, because on real problems that's not possible. The games we're interested in cannot be pre-computed all the way to the end. The games and problems that can be computed to the end are called solved, but we want to be dealing with problems that are not solved. We want to be good at winning games that are unsolved. And again, I mentioned chess, shogi, go, go-bang, and many real-world game examples here. So that completely changes our mindset, because we now have to make exploratory moves. We have to explore. We have to use some trial and error, otherwise we don't know what gives us a reward. So we have to make exploratory moves that would be considered a waste in a pre-computable framework. So you don't know what you don't know. So we have to kind of find out what we don't know and what gives us a reward. So we have to include such moves or positions as they meet to solutions that we understand only later to be optimal, right? We have to do some trial and error. You can't get there unless you include them in your path, and you can't get to the destination without walking on the path to get there. In other words, top-down is not possible. Even a complete bottom-up is usually not possible. So I want to make a side comment before we leave this completely. I want to point out that quite often things are called a retrograde analysis when we start at the end and work our way forward. And a good example for that, I think, are the table bases in chess. So they are used in order to make it possible that a computer chess game can bias the gameplay towards getting to a position from which you have a guaranteed win. These so-called table bases have been computed for 6 pieces that are left on the board in the endgame, and partially computed for 7 pieces. The combinatorial explosion is so large that for 7 pieces this has not been fully computed, but the table base for 6 pieces is complete. So that means we start at the end, we start at the winning positions in chess and work our way forward with what is called retrograde analysis, because we want to be able to find a path towards a position that is guaranteed to be a winning position. You still have to make certain moves. You still have 6 pieces on the board, or you still have 7 pieces on the board if you find a position in a 7-piece table base. But it is quite useful. It is really quite efficient when you can start at the end and work yourself backwards in a way that is also top-down, except here we are using pieces. We're not using moves, right? With Tic-Tac-Toe we've used moves. We've not counted pieces. A table base is really a set of strategies to use when you have a certain amount of pieces left. Okay, I'm not going deeper into it, but many of the top class chess programs such as Stockfish use table bases internally. DeepMind's AlphaZero does not use table bases. It doesn't need them, but it could be enhanced with table bases, and many programs use table bases. Stockfish, for example. All right, I leave this out at the moment. Please stop the video or download the file to read this in detail. I'm just saying top-down is a viable and frequently used method. Okay, so when the state space still fits in memory, we can do this. We can do these table methods. We enumerate everything and go backwards. So what we do is that we assign a certain value to every state. We can consider this a desirability value for that state, right? We enumerate all the possibilities of states that we have. We can still fit state in memory, but we cannot fit all the paths in memory, right? Because the paths are a huge combinatorial explosion. We still have the states in memory, but not the paths. This is what we saw in Tic-Tac-Toe. We have a certain fixed number of states. We have less than 700 optimal states, but we had something like 282,000 paths. So we can enumerate all the possible states and assign them a value. We consider the desirability value for that state. We just cannot fit all the paths in memory, and we would have to go over the paths bottom up in order to find the winning positions. So what we do then is assign this value, and we then play many games of this game, pretty much random games. In each game we update the value for the state, and we do that, for example, by assigning a value 1 perhaps, right? It doesn't matter for this simple case what it is. It can be 5, it can be 10, it can be 1,000. So let's just say 1, then we could later also develop a certain probability analogy. We assign a value of 1 to every winning state, because if we are in that state, we have already won. So the probability of a win is 1. And any predecessor receives a starting value of, for example, half, right? 50% of winning or losing. We just assign it a value of a half. It doesn't have to be a half. In this case, it makes sense to pick a half, but sometimes a better value would be 0 or -1 or -10. In this case, let's just say when we don't know yet if it goes to a win or a lose, we call it 50%, so we assign a value of a half. And now we keep playing many of these games, and then during the gameplay we update a value that is now somewhere between the current state and the next state. And this is explained with this formula. So v of st receives an updated value, and that is the old value, v of st times the difference between the next state and the current state, right? That is v of st plus 1 minus v of st. That's why this is called temporal difference learning, right? We are one time step afterwards, so that's the temporal difference. And this difference between the values of these two states we multiply with a certain factor alpha, and this now represents a certain distance between the current state and the next state. And this is what we increase v of st by, and call that the new value that we assign to the current state. So we compute the value for the next state, but the update is done on the current state, v of st, not the next state, right? We are backing up the value by using the temporal difference between the current state and the next state. With alpha, we are now somewhere between the next state and the current state. And alpha is usually a small number, but it does give us a little bit of a distance between the current state and the next state. So we're moving somewhat towards 1. We start with a half and move a little bit towards 1. That makes the state a little bit more desirable, right? So we're getting closer to the winning position. That's why we should call the current state, not the next state, but the current state a bit more desirable, because this state is a bit more closer to a winning position. So when we do this, alpha is a certain proportion between the current state and the winning state. And as we decrease alpha over time, we are actually guaranteed an optimal convergence. So we back up all the states as we play many games and update the value. And as alpha goes to 0, this is guaranteed to converge to an optimal solution. And keep in mind, we want to explore many things with reinforcement learning. If this so-called step size parameter alpha is not reduced all the way to 0, then this computer player also plays well against opponents that slowly change their way of playing. We somewhat have to model the way the opponent plays. So in this model, we just use random numbers or just random decisions. We just use a random decision that the opponent plays. But that's not how this would be in a realistic game situation. The opponent may play better than we do. It may be smart, maybe stupid, and maybe random, right? So what do we do when we have an opponent who plays a certain strategy at the beginning, but over time changes that? So even though for alpha towards 0, we're getting an optimal solution as a convergence, we want to keep in mind that the opponent may change his strategy. And when we don't make alpha too small, then the system still plays well against an opponent that slowly changes their way of playing. Okay, so next I want to explain this with a tree. So we start with a certain starting position A, and now the opponent makes a move, and that brings us into position B. And now it's our move, and we have a bunch of choices. So for our move, we could, for example, go to position C, and C is optimum. That's what the star indicates. So our move C is the optimal move C star. And the dashed lines represent all our choices, but we don't pick anything other than the optimal move. We have C and C star. And whenever we have that, we back up the previous position A, right? The red arrows indicate the backing up. Now it's again up to the opponent. Now the opponent makes a move. We have no influence on this. So the opponent move is always a straight black line downwards to the next one, and then comes our move again. And again, the dashed lines show our choices. And here the optimal move would be E star, but we don't pick it. At this point, we don't want exploitation, we want exploration. So we pick another move, E, but one that is not optimal. And you see that we're not updating here. There's no red arrow from E to C. There is none here. We didn't do an update, we didn't do an exploitation, we chose an exploration, so there's no update rule here. But then again, the opponent makes his move, straight line E to F, and then in our next move, we are again making an optimal move. Our G is going to be G star. G star is the optimal solution. We pick it, so it's time for an update. So E gets updated based on G. All right, so we have two cases where we have an optimal move and one where instead we choose to do an exploratory move. So I explained this here. This is a sequence of tic-tac-toe moves. The solid black lines represent the moves taken during a game. The dashed lines represent moves that we in our reinforcement learning player considered but did not make. Our second move was an exploratory move. So we are going to another sibling, but we don't pick E star, even though it was ranked higher. So the exploratory moves do not result in any learning, but each of our other moves does. So this is how we are making these decisions here. And when we're now doing this, I will follow this pattern. I will make the first one and the last one optimal exploitative moves, and the middle one not as an optimal move, but an exploratory move. So I've written a function make move, and you see that at the end, values of state is values of state, that's the number we want to update, plus alpha times values that is representing by our own next move minus the values of the current move. This is exactly the formula that we had here. This update formula in the values. This is exactly how I make this update in the values association. All right. So this function works by first finding out all the candidates that our opponent has. And as the opponent makes the next move, these choices are where there is an empty space. The field hasn't been filled yet. And next we replace them with an O. That's the move that the candidate moves that our opponent has. And the distinction between exploitation and exploration I make with random numbers. So if a certain random number that goes between 0 and 1 is less than the opponent probability, then we are taking an opponent who plays like we do. We are maximizing the value, and if it is not less than the opponent probability, then we pick a random choice. So this is a random choice player. Then next come our own moves. Again, we find out all our candidate moves. Those are the ones with an empty field in them. And then we pick all these candidates where we can place an X. And here I do the same thing now for our own move based on probabilities. So we take a random number between 0 and 1. We check if it is larger than our own probability. If it is, then we go by value. So we want to exploit and not explore. And if it is above that, then we pick a random choice. So here we want to explore and not exploit. So with these two probabilities, own probability and opponent probability, I can set to what probabilities these moves are going to be exploitative or explorative. So in this case here, this would be this would be a 1 and a 0 if we want to pick C star. The opposite when we are picking E not to be E star, and here we are picking G to be G star. Okay, so this is now the make move function that I use in our gameplay. So here we do the same as in the tic-tac-toe move pictures above. The first move is greedy, so I have 100% probability here because we want to take the maximum here. So I have to pick 100% here or 1, right? So a random number between 0 and 1 is less than 1 with 100% probability. And in the second step, I set it to 0. So in this case, then it's going to be a completely random choice, just as we do here. Our E is totally random that we have here. And then in the third one, I pick again with 100% for our own move. So we are going into this branch where we pick a random choice of the maximal values. Okay, so this is greedy, not greedy, greedy, or exploitative, explorative, exploitative. So let's run this 100,000 times. You see that I'm running 100,000 games here. And let's look at the pattern that we get for the computed values. Again, values is an association here. I give them an initial value of a half, and for the optimal choices, I give them a value of 1. Okay, and I start with a step size of 1 over 1,000. So we start out with all the feasible initial moves. That's an empty board, and we start with an X. We go first, we are X. So these are the 9 choices that we have to go into the game. And here as well, we start with greedy for ourselves, and the opponent makes random moves. All right, so we play these 100,000 games now based on these rules that I have set up for our make move function. And this will give us, as a result, a values association that we now are going to use in the future to actually play those games. Right now, we are only playing these games in order to get values, right? This is the only purpose why we're playing these 100,000 games, because we want to have exactly this pattern for our values association. But we haven't applied them yet. We are only creating values now because we want to use this table method in the applications in a moment. So we see that several of them have a value of 1. Most of them still have a value of a half. And there are some that are between. They have now received updated values that are between a half and 1. That makes them more desirable to pick towards an optimal solution. But only the optimal solutions have a value of 1. So let's pick a random starting position, and I pick, just without any specific reason, this particular starting position here. And we can see that the values larger than a half are closer to a win position. In fact, the last several values in that list are just 1x away from a win. So let's look at them. So anything larger than a half is from here onwards. And you can see that they are all almost winning positions. For example, here we would just have to put an X and we win. And not here, but here we would have to put an X and win. Here, put an X and win. Here we put an X and win. Now, the opponent can still destroy that because this is 2x, 1-0, right? We've only gone 2 steps here, so this is still only 2x, 1-0. So the opponent can still destroy that. If the opponent goes in between here, say the opponent makes an O here, then we're not having an immediate win, but we can still continue playing. But still it becomes clear that these types of positions are much more desirable because we already have 2x in a row, column, or diagonal, right? Here we have 2x in a row, here we have 2x in a column, here we have 2x in a diagonal. So they're already somewhat close towards an optimal solution, but the opponent can still destroy that. We only have 2 so far, but we already have several of them that have values larger than 1. Okay, so let's continue this. So now let's do 4 steps, look at them. So we have, okay, this is gonna be a much larger list now. We have more than 1600 now, and we can see that all the ones with a 1 are already winning positions, right? Everything that has a 1 here, you see that we already are winning. We have 3x in a row, column, or diagonal. So let's throw them out actually. 3x, let's throw them out to see what we get. We want to delete those cases where we have a 1, and we can see that the numbers larger than a half are again the more desirable positions. We could place an X here if the opponent allows us. We could play an X here if the opponent allows us. They are more desirable, but still the opponent, of course, can still destroy something. But we are pretty close to winning. For example, if the opponent makes an O here, then we can win here. If the opponent makes an O here, then in the next move we can make an X here. So we are somewhat more desirable in these choices, which is why these have numbers larger than a half. Everything that is still a half is not so desirable. We are not so close to a winning solution with that. Okay, so let's look at the list line plot. We have a bit more ones, as we can see here in this list line plot. How about 4x? We are gonna get the same picture. We're gonna get the same story. Now we have made several more moves, and we can see that we're getting more ones here. How about 5x? And 5x is the ultimate win because we cannot put more than 9 positions on the board. So we have many more ones here and only a few draws. So let's remove the ones from the 5x. And what we're left with is all these positions. Okay, this is now a little bit hacky. We can definitely improve this. I just want to be quick and dirty at this point. And here are all these situations that really don't help us much. Let's see if any of this is an opt. So member queue of opt and hash. That's gonna be a big one. Let's take the union, and none of them is an optimal. And if I take the cases and not the delete cases, then we have all of them an optimum, right? So here we have the value of 1 being the ultimate determinant. We have that here with 5, because with 5x we really are ending the game. There is no way to go beyond that. Okay, so next step, let's compute the winning solutions with the values. We haven't used values really in a multi-stage game. We are interested in using values to make the real gameplay. So let's use this now. And when we just use a few steps and we are using values as our guidance, then we are pretty quick usually. We usually win with 3x no matter what the opponent does. So here we looked at a guaranteed win. We have this at the end with these 5x, but we're also interested in a quick win, and we usually get this with 3x's no matter what the opponent does. And the following, we could use TD or BU, and TD of course would be better and more efficient, but in big problems we won't have it. So I'm using BU at this stage in the gameplay. So we first start out again with our 9 possible positions that we have, and I want to pick the one that is maximal by values. Okay, so that happens to be this one. All right, so next it's the opponent's move. So he places an O there. This is a random choice, so let's assume we have an opponent who is about average. Again, we play with the maximum values. We place another X where this is most suitable for us. We have a random move from the opponent. And now comes the interesting part, because now we have 3x. And with 3x, this is the first opportunity for you to win. And is it an optimal solution? Yes. Right? So we won pretty quickly just by taking values all the time. Yeah, values here, values here, values here. We've used bottom-up, and we won already with 3 x's. Right? This is because we always picked the maximum value that is available for these values. Okay, so let's put this into a more loopy structure. So let's put these together, and I run it a few times. So usually in this case we win very quickly with only 3x and 2o. So it's gonna take probably, hopefully a while until I get the first false here. So let's play it a few times. 3, 4, already 1 at 4. Let's try it again. 1, 2, 3, 4, 5. We have to run it a few times in order to get a false, because the probability is relatively low. So okay, after about 15 times or so we have the first false. But now we are still guaranteed that values is going to help us. So according to all laws of probability theory, we should now be finished with just one more. And we have one again here, right? Just one more, and we are winning with 7 fields filled. That's 4x and 3o. So let's do it again. Let's try a few ones. Let's see how long we need for the first false. Quite a lot of them. And so we have the first false there. Typically we just need to do one more iteration and we get a true and have 1. Okay. So now let's play 100,000 games with our temporal difference learning strategy, and let's keep counts. So 3, 4, and 5 are the number of times that we won with 3x, 4x, and 5x, and I'm also counting the lost games. So let's play this 100,000 times, and I store these totals of 3, 4, 5, and lost and outcomes. And then I total that vector just as a sanity check. This needs to be 100,000 again. We want to make sure that every game counts. So the total here should be 100,000. And then let's look at a pie chart of all these outcomes. And we want to see how many we are winning with 3x, 4x, 5x, or losing. So these percentages will give us an idea of how successful this strategy was by using values. So we get 63 over 83,000 for 3x wins. We get, we lose over 2,100 games. The check is okay, we have 100,000. And here, when we are computing this as a pie chart, we see that 2.1% of the games we're losing. right? So we have 83% we are winning with 3x, 12% we are winning with 4x, and 2.6% we are winning with 5x, and 2.1% we're actually losing. Okay, so this strategy is definitely not perfect. Keep in mind, even AlphaZero has lost a few games. It has lost both as a black or white. So the strategy is not perfect. We are definitely in the situation that we have to accept a couple of losing games, but it is still a lot, right? If we subtract these 2% that we're losing, then we are winning in some 97.8%. Okay, so with that said, we can certainly still improve this a little bit more. We could run more training games, for example, 1 million. We only used 100,000 here. We used 100,000 games to play, and we used only 100,000 in order to obtain our values function here. That was also only 100,000. So we can certainly improve that by running more games. The guys from DeepMind that were winning with AlphaZero were playing, if I remember the numbers correctly, something like 80 million chess games, 80 million random chess games. So you have to play a lot and a lot and a lot in order to learn your values functions. So we could do much more. We could play 1 million games or even more. At that point, you would have to start using parallel computation. Everything here I did was single-threaded. But if you want to go higher, then you would have to start going into parallelism. You also want to use compilation. We can use C compilation with compile, the compile function we have since version 8. We have a new function compile in version 12. And that goes all the way down to the assembler that we can study what we have compiled. In that case, I suggest you avoid the string representation and do everything just with numbers and don't use strings. I just used strings here in order to explain the positions better. I think it is more visual that way, but you would then use compilation and avoid the strings. And you can further decrease alpha. That gives you a more exact play, but at the same time, you're also not benefiting from exploration, because if your opponent changes strategies, then a small alpha will be more exact for the optimal solution, but not adapt to changing gameplay of the opponent. And you change the exploration versus exploration parameters. I've done that with percentages. You can set that up any way you want. You can use 100% and 0% as I did here. You can use 70-30. You can use 60-40. You can use 31% versus 69%. You can use any type of distribution here on these probabilities. And another way you can improve this is you can exploit symmetry whenever possible. This will reduce the combinatorial explosion that you have. For example, these cases are really all the same. You just rotate the board. Northwest is the same as northeast, is the same as southwest, is the same as southeast. And northwest, east, and south are the same, right? Those are really the same positions. So you can definitely reduce the entire set of possible combinations by a factor of 4. Okay, that brings me to the end of today's session. I hope you had as much fun with this as I had, and I hope I see you again in one of my next sessions. Bye bye.